the information of today's session. So we have 3 speakers in total. This session is hosted by IEEE Photonics Hong Kong chapter, and Professor Xian Kai Sun will preside and moderate this journal club event. So after each talk, there will brief Q&A follow each presentation. So there will be time for 1 and 2 questions. After all the speakers give their talks, we will have a panel Q&A following. So with this, I would like to hand over to Professor Sun. Shen Kai,
Right.
yeah,
Yeah,
can
can you
you
all
take
hear me?
over? Yeah, we
Okay,
can hear
great.
you well.
Yeah, thank you very much for the introduction on this IEEE Photonics Society Journal Club. And so our next speaker will be Mr. Fu Kui. Is that correct? Well,
I thought I'm the third presenter, I guess.
so do we follow the normal order or
So I would do Patrick first, the review of the Silicon Photonics Technology platform
okay,
developed.
so we just follow the originally
Yes.
planned order. Okay, great. Okay. So now first speaker will be Dr. Patrick Low. The title of his presentation will be Review of Silicon Photonics Technology and Platform Development. So let me briefly introduce Dr. Low. Dr. Low received PhD degree in electrical and computer engineering from the University of Texas at Austin in 1992. He was with Integrated Device Technology Incorporation USA on silicon CMOS semiconductor manufacturing areas in process and integration R&D. From 2004 to 2017, he was with IME A-Star Singapore, where he was the laboratory director and program directors of nanoelectronics and photonics program, and subsequently the deputy executive director of the institute covering R&D. Since 2017, he co-founded the company as Advanced Microfoundry, focusing on silicon photonics manufacturing technology, industrialization, and commercialization, being the president and now as CTO. He was the recipient of IEEE George E. Smith Award for Best Paper Published in IEEE Electronic Device Letters in 2007. He has won both Singapore's National Technology Award and President Technology Award for his works on nanoelectronics and photonics in 2008 and 2010, respectively. So without further ado, let us welcome Dr. Low.
Yeah, thank you very much. Let me share the slides first. Okay, great. You can see it. Yeah. Thank you very much, Chairman. We are very honored to participate in this very interesting event, as Dr. Chen has expressed. There are many interests there. There are many useful points. I think it's a very good event. Congratulations on this. So we are very honored to participate in this to discuss our recent published articles on the topic of silicon photonics technology and platform development. Along with me is Dr. Lu Xiansu. Both of us actually were the co-founder of the company of MF. So before I start, I'd like to acknowledge the manufacturing team at AMF, as well as the previous IME A-Star teams for many years of hard work for the development of silicon photonics technology. As many of you might have known, we started activities over 16 years ago. Start from one of the technical R&D programs in A-Star. And also to our current technical staffs and previous members, wherever you are, and all the credits are yours. So we would like all to thank, it's very important actually, we have to acknowledge all the industry partners for building the silicon photonics capability demands together throughout this journey with us for the patients and also their strategic interest. So as what we've seen from today, from one of the tech R&D programs all the way carry on to a commercial with the entities now. So here's the outline of the discussions. So basically, over the past decades, we have seen a tremendous R&D activity and various resulting application exploration, particularly the product being commercialized based on the silicon photonics technology. As you see from various technical reports and business reports, the penetration rate or the adoption rates of silicon photonics in competing with the 3-5 based has been increasing from last couple of years. And this actually gives a lot of confidence and credits to the other emerging applications, because all the applications that we are looking for will eventually we're aiming for commercial purposes. So it's very important that we see the events as the commercialization taking places with the increasing adoption. This is very important. So in this talk, we'll discuss the following. Firstly, brief on the history of the silicon photonics development, then on the present status of the silicon photonics development and commercialization progress, with the highlight of the various foundry service activity worldwide, including MF work to the silicon photonics community development. Secondly, we will review the typical device library offers, but I will skip some of the technical contents in detail because all of those have been described quite extensively in the manuscript already. So then next we talk about the quality control systems, because this is relating to the testing capabilities in any of the foundry, because this is very important beyond from the lab-based production, lab-based experimental lines towards the commercial with the foundry lines. So quality control and testing are a very important part of it. The last points I want to touch upon is we call it the last technical matter, last mile towards the final productizations, which is always interesting. Is on the technology of photonics related with the packaging. So because the co-packaging has been a big buzzword nowadays in the community towards the product. So few disclaimer here. So it's not the purpose of this talk to compare or to conclude various service providers for who is providing the best. This is not the purpose. Neither it is the intention for me to advertise AMF. So excuse me if I inevitably introduce some of the AMF in the sense of marketing, but it's not the purpose. So I'm only use it for the example to illustrate the whole cycle and also service around for making of the silicon photonics from the design to materialize it as a meaningful exercise. So the silicon photonics begin with the seminal papers by Soref, and all of you know this back to 1987. So describe a very interesting phenomenon, very useful phenomenon, is the free carrier dispersion effects in silicon, which forms the very idea of the first building blocks of the integrated photonics circuits, which is the phase shifter. Then subsequently, many university and the research institute create many type of useful devices towards the full silicon photonics PIC solution. I say full actually is quote unquote, because every day and now we start to seeing new devices being reported to adding to the overall functionality, what the silicon photonics platform can be. So the first is always the high waveguide. The reason I talk about this whole cycle here is because I think for the interest of photonics, because they have a different wavelengths. For any of the wavelengths that we talk about, it will go through that cycle. The first one is always the high quality waveguides. You want to get in the confined lights, getting a low loss. And what's importantly is that the high quality waveguides with the confinement of lights in the vertical directions, so that the lithography can define the waveguide in the plane. And the original SOI waveguides were comparatively large in several microns in width and thickness, but eventually thinner SOIs, for instance, the 220 nanometers as the de facto was used by majority of the groups. Although we still see a few different types, but all somewhere around 220 or similar to 170 towards a 500 nanometer in their range. All of them give a good performance of a lower loss, tight bending radius, and many type of other passive devices. The choice of the thickness were purely based on what's the emphasis on the specific application purpose. So meanwhile, there was also a great milestones of the Alexander interferometer modulator with the first high-speed demonstration in 1 gigahertz based on the plasma dispersion effects reported by Intel. And the parallel development was the germanium integration into the waveguide photodetector schemes. And also the wafer level high quality germanium can be processed as we doing now, like for instance, the AMF, we're doing this routinely. Now the silicon photonics, the chip is almost complete except the laser. So the main approach on the laser part of it is in the following. So laser integration into the silicon via packaging, either through on-chip or off-chip. Of course, the choice of either is largely determined by the technical performance needs, cost, and even availability of the accessibility. So silicon and germanium engineering for lasers has been very hot in the past. These are all wonderful scientific topics, but not so far being successful. Lastly, as the technology inched towards the market, work has begun on the next stage, which is the packaging for silicon photonics product. This can be further split into 3 aspects of it. One is the photonics I/O interface, the electrical I/O interface, and also the integration. See the intercompatibilities of those I/O interface can be integrated all together. So all these demands and support and gradual establishment of a long stretch of supply chains. So I'll say I feel those are quite very challenged, not only in a simple engineering or science problem. Some of them could be material related, because Dr. Summers mentioned there's a large community, so that in the attendance here, there are students. So actually, this is very important for the students to realize, although the silicon photonics reached to the product stage, this is only give us confidence. I mean, joking here, all of us have a great opportunities of getting a job, that's for sure, and also long term of the job securities. But what's also important, there's a lot of intellectual curiosity in the science topics, how we're going to do it differently. Because as we see more and more on the packaging, I keep on saying the packaging, because for product, this is a very, very important part of the piece. Last step to complete it, to make all the works meaningful. Because without the packaging, without the product, everything that we are doing will remain in the science domain. Okay. So this is talk about the silicon photonics ecosystems. Although quite a bit of the silicon photonics activity finally reached into a commercial stage, it already has a reasonable ecosystem, because it's largely leveraged on the traditional silicon industry. Not ideal or optimized, but possible and works to some degree. Although we face quite a bit of a pains, like managing the supply chain, but it's workable. But I think it's also intriguing, especially in the last few years, as we're facing the COVID situation. The supply chain management become a serious issue. So it's very important for any of the service providers to think about it, how we can link up all the supply chains and make it easier for the final product users to manage it securely and also easily. So already a big players in the datacoms and telecom space have their own internal silicon photonics programs, and this includes the integrated device manufacturing idea. There's also a very healthy space for silicon photonics startups, design house, fabless, so on and so forth, which include many in the different levels, such as the design house, IP developers, application includes the quantum computing, artificial intelligence in the various, and also like for instance, the LiDAR, sensing, all those. Additionally, there's the healthy infrastructures of software part of it, which is ADA supports optical simulation dedicated for optics and photonics. All those become viable for silicon photonics companies or startups with reasonable investments to design their products with a purpose-built software, fab them out in a commercial foundries, package the singulated dies, and then finally launch their products. But you can see the criticality of the prototyping lines to pilot lines and to the industrial fabs, along with the so-called broker agent design aggregators who may add their own values, link all the activities as much as possible for design support and testings. Lastly, and don't forget the tool makers, especially testers. We work a lot with the testing developers on the hardware as well as software. So given what I described above, you can see there are many foundations have been set, and yet there are huge rooms to be filled to truly link all those whole ecosystem together to form a true photonics product purpose, the supply chains. So currently, it's more or less is dependent on the legacy supply chains or the existing supply chain based on the CMOS, which is not optimized, as I said. So we need a true photonics product purpose, the supply chain. For students, I would say in the future is very bright and exciting, calling for innovations to go beyond what the electronic supply chain dominated at the present stage. So next we'll focus on what wafer foundry is about and does. Yeah. So before we survey on various platforms, offers, and PDKs, I use the AMF platform as an example purpose, just to describe the typical layers and content so we can appreciate more what others are offering in the proper context. So from the bottom up, you can see there's SOIs, silicons, nitrides, all those. So in those platform options and different differentiating features, so you have the silicon nitride on bulk or silicon nitride in the front end and germanium SOIs, or the silicon nitride in the back ends and germanium, or the combination of it. So in our case, actually, we provide the standard MPW versions. Many probably have experience already that with the nitride backends and germanium on the SOI. So the SOI that we provide, majority is based on the 220 nanometer silicon. And also we have two versions of a 2 micron and 3 micron barrier oxide, depending on the specific needs. And also the other thickness in processing that can be discussed in the customized flows. So that includes the silicon phase shifters, both in the ring format and also in the Mach-Zehnder interferometer formats. And germanium fold detectors in both in the lateral and the verticals. And also one of our options can be co-integrated is the waveguide based APD device. With silicon and nitride edge coupling schemes, and also with the grading for the waveguide, the wafer level testers. And also we have the thermal optical shifters based on the doped silicon or the metal with or without the undercut for the thermal efficiency consideration. And also we have the option for our oxide cladding removal options because there are certain application will demand the oxide removal. Then the last several features is on the V-groove and also laser attachments. So those were taking care of the optical interface. And also the last will be the UBM solder options for the electrical interface. So according to the application needs for each of the functionality performance, so we can trace it through the existing so-called technology trees to identify the right platforms or the combination of each devices and technology to customize your own flows, own platforms that will make it into a product. So on the typical foundry services, there are three different types of fabrication service that's the most the foundry provides. One is on the multi-project with us, which we call the MPW shuttles. So this is all based on the fixed integration flow with the cost sharing, and also make a lot easier for people who have a repeated needs on the designs, and also the easy to use standard PDK device that we offer. Then the other one is the customized prototypings, then be able to customize the integration flow as what MF has been providing to our customers, to the community so far, for the customized integration flow per application needs. So this may include many things, but not limited. But and also very important now is the volume production steps, regardless small or big volume. It's all about production stay in and out, and eventually all the R&D exercise, R&D practice will eventually get into their mode. So on the as a typical foundry service flow, as I described in on the left-hand side, it describes the typical development steps from design concepts to silicon chip materialization. This describes clearly the role and the responsibilities of the designers, foundry side of design support, mask shops, and also foundry fabrication, typical testing. So designers is on the concept, schematics, simulation, design, and GDS layout. Although we provide the initial foundry provides the silicon proven standard PDKs, process design rules, and also the DRC check on the DRC, make sure the DRC cleanness and the process compatibilities, or at least to flag out if anything are not compatible or any prone to mistakes. So fine tuning and DRC recheck and final handshakes to be ready for the tape out. The mask shop will just do the mask making and then to the fabrication. As you can see, and also probably have experienced it before, the longest cycle time is always in the whole exercise. And the most expensive ones is the fabrication. So these 4 steps constitute a full iteration cycles for any of the designs towards a silicon chip. So any steps within has to be done very, very carefully, because any flaws in any of those steps, even minors, can be fatal and also can be a very catastrophic to all your project management. This is why it's very important for us to be very patient, especially in the first stage on the GDS designs, because without the right GDS, everything's off. Fabrication, although you can refabricate it, take time, but if it's a design flaw, everything's off. So this is why for any of the production preparation, design mask has to be tested out more than once to ensure we can freeze the designs and process on all corners, managing and manufacturing the variabilities before committing a large quantity of wafers. It becomes a very expensive journey. So this table provides the information on the available open access silicon photonics technology platforms globally based on the public information. So again, the purpose is not to survey who is the best and so on and so forth. So, but I'm just to describe it here, what is available there, because I think all the smart users today, they are smart enough to choose what they are looking for, and detailed information has been already documented in the manuscript already. So again, one of the disclaimer is the table is not exhaustive. In case I miss out anyone you think it's important here, I apologize here. Okay, we list the MPW design areas for different foundries, the chip size, so on and so forth as the minimum unit or the minimum orders. The cost tends to be around $1,000 US dollars per millimeter squared for most of the standard active offerings. So as it's showing in the table, most of the foundry adopt the thin SOIs in the range of 170 to 500 nanometer, and the majority are the 220 nanometers, with the waveguiding silicon layers not exceeding 500 nanometer in thickness. So this is therefore will support the most size in the sub-micron range, which is ideal for most of the application that needs a compact and high-speed devices. But of course, there are some organizations that offers the thicker SOIs, which is like 3-micron SOI. so on and so forth. So of course, they have their own special needs and special advantage to it. But one of the things, like for instance, the modulation formations can be quite difficult, but has been demonstrated possible also. So those you can see at the top. So before I go on for the next stage, I want to share you a little bit about the which I'm not sure that I described in the manuscript, is on the visible platform. So we and partners have been working on this for quite some time to develop a sizable device libraries for visible wavelengths based on the silicon nitride. The application of silicon nitride in the SOIs for O-band and C-band has been described in the manuscript already, but this one is on the visible. So because more and more the application, I think, will include for like optogenetics, fluorescent excitation, sensing, spectroscope, and even for quantum integrated photonics due to the source difference. They all demands a different type of wavelengths. And also we've seen very near distance communications, free space sensing as a LiDAR. So all those will require the platforms goes beyond what the O-band or C-band. So this is what we are working on the visible now. I think this is probably is interesting to the student community also, because there was a heavy explorations in the application domains, what the integrated circuit can do. So this is certainly is not limited to O-band and C-band, because these are two predominant in the data center per se, but I think the application more emergent actually beyond those. Next slide. Yeah, so this slide provides a typical view of the type of devices, include the PDK library for designers to access on to putting it together into integrated circuits for their functional needs. So this using using MF example again for providing for 400G ready design kits. So of course, the modulated and fold detectors are important active devices for coding and decoding information for the optical and the electrical signals converting back and forth. And also there are various passive devices that perform the optical functions for filtering, delay lines, phase control, so on and so forth. Now also important is the photonic IOs, coupling the devices but required to couple the light in and out from the external laser and the fiber. Right. So let's go on to the next steps on the typical PDK. I think the detailed description is in the manuscript again on this. So let me, yeah. So let me just say a little bit words about what the PDK that means. So in here we report the performance for both gradient and edge couplers wherever they are available, and then conventionally to ensure the performance of such like a PDK device libraries to be successfully implemented day in, day out, the end users needs a very stable integrated photonics lines as well as several rounds of trials prior to actual productions. To simplify the development routines for all the users, typical foundries that includes AMF provides PDK device libraries which been tested and developed on the design of the experiment approach with process corner checked, with plus minus variation checked, and optimal designs that was presented, so on. So the device, as I mentioned, it typically has a passive device, both in the silicon and nitride, and the active device is modulation and fold detector. Then all those will, as I listed in the few columns here. So typically those are the components can be put in together to satisfy most of the application needs for various type of functions that realized in the photonics integrated circuits. So this slides demonstrates the efforts in the development of our technology platforms with few versions of the PDK release. The last version, the latest being the early 2022, have been released that already. We call it the PDK 3.2. So MF PDK contains 6 libraries. So we can trace through the technology trace structures to define what's the right platform for what application. But what's listed here is the MF platform contains the 6 sets of device libraries that can be implemented on the MF 5 integration platforms in through all those mutations. So again, each of the PDK cell we exempt with corners, manufacturing the variation tolerance, and updated with multiple runs upon each new release. So on the design side, upon the availability of the PDK device cell, in our case, we have been working with multiple PDK vendors for providing an ecosystem for silicon photonics PDK development, as well as the PIC designs, from the physical views of the layout to the logical view of the schematics. For GDS generation, typical foundry will make the PDK available more than one EDA tools. For instance, on the K layout, mental graphics, Lucida, Synopsys. So at least these are the availables in our case. So furthermore, in particular on the K layout, we have developed integrated flows between the K layout and numerical interconnect. After the GDS generation in K layout, a netlist can be extracted by using this integration flow and then imported into a numerical interconnect. Then the optical circuits can be automatically built by connecting the schematics in the numerical interconnect and ready for circuit simulation. So this flow is also called as a layout-driven schematic, which is essential for high efficiency designs of large-scale silicon photonics integrated circuits. So for foundries, one of the key criteria, very important, is the quality control systems. So for full implementation for quality control and quality assurance, inline inspection and data collections, fab mainly on the process SPC controls, like for instance, the silicon nitride CD controls, thickness, so on and so forth, and the layer-to-layer overlay specification controls. So prior to any of shipping, there always been a wafer level testing on electrical and optical performance, as an example showing the channel waveguide propagation loss, for instance, and also for the yield improvement along with the electrical testing and optical testing and data correlations with specific yield maps. Data defect inspection has been also inserted in the process steps at the necessary stage to make sure the process lines clean. Any of the issues can be caught much earlier in the lines. So of course, we need various types of tools. So one of the very important tools other than the defect inspection is the testing. So in our case, we have the inline wafer level testings, and towards the final wafer out, then the non-good dies in the chip level, in the wafer levels. Then the other one is on the chip level as well as the packaging for the reliabilities. So this is the slides is very similar to what I described previously. Again, the last box is always the last level of quality assurance, which is a very important one to touch upon the yield understanding and the yield improvement. So for, as I mentioned, the last mile is always the most important one. You when you talk about 10% or 5%, you probably will take equal amount of time for what's competing on your 90% of it. So for packaging purposes, so this is what all the toolboxes and device library that we provide. So on the edge coupler structures, we also set up the modules for integrated V-groove for passive fiber array assemblies, fibers, even for single fiber assemblies. But similarly for laser and amplifiers. So routinely we provide supports to customers with UVM bumping and a couple of things. So here's the example of what we did previously to simulate what the electronics and the photonics integration. This one has the interposer design and fabricated down below, and with the both photonics integrated circuit and several of the electronic circuits, all of those are being flip chip onto the interposer substrate itself. So what the picture you have seen, actually we have done this many years ago, back to 2016, is the dummy electronics chip flip over a photonics based interposer. So this device itself already shows the 56 gigaball modulation rates. So it's well set for the 400G device. So foundries are in the conclusions. So foundries should be your most trusted photonics production partners. So for examples, like we have been in the business for this, being for many years, being the pioneers of silicon photonics, the development. We think we are spin-off from the A-Star. We have the complete manufacturing lines and also been processing products actually in the field deployment for the last 5 years or so. So we, with all the PDKs, as I mentioned, with the full silicon proven, and also we continuously develop and improve the PDK, and also the custom design supports and multiple platforms that I mentioned in the technology trees in offerings. So focus now is on the fab capacity ramping up that will taking care of the business for the volume manufacturing, particularly on the online stability and quality, and also cycle time. But all the students are probably very curious about the cycle time, for instance, because all the PhD stations more or less it depend on where the chips being available and tested. So supports various application and markets, and also the more capacity and the advanced capabilities is in the progress in our case. Okay, so in here, I'd like to acknowledge all our customers for their long time support and trust to build these industries all together. And also thanks for all the student communities that whoever they being the shadow runs in our MPWs. They actually give us a lot of inspirations and encouragements to our teams to understand there are many, many explorations on the applications that people have not thought about it 5 or 10 years ago. So this is very encouraging. Yeah. Thank you.
Thank you so much, Dr. Low, for your wonderful presentation on reviewing the silicon photonics and also the capability of AMF foundry services. So due to the time limitation, we just move on to the next speaker. So our next speaker would be Dr. Mengyue Xu. Her title of presentation is High-Speed Modulator with Integrated Terminator Resistor based on Hybrid Silicon and Lithium Niobate platform. Brief introduction for Dr. Xu. So she received a PhD degree from Sun Yat-sen University. Her research is mainly focused on integrated thin film lithium niobate photonics and heterogeneous silicon TFLN photonics. Without further ado, let's welcome the second speaker, Dr. Xu, please.
Hi everyone, I'm Mengyue Xu from Sun Yat-sen University. Today I'm like to talk about the high performance hybrid silicon and lithium niobate electro-optic modulators. With the development of next generation communication technology, modern optical communication networks comes a bandwidth crisis caused by the continuous growth of global IP traffic and the energy crisis caused by the increasing electrical consumption. Therefore, we are challenged to exploit the speed and capacity, also reducing power consumption. And sorry, wait a minute. I think I have some problem with my PPT slides. Hi, Hatsu, can you share my slides for me? I think I can't move the slide forwards.
Okay. So let me. Can you exit? Can you cancel slide share?
I also recommend maybe just don't show it in slideshow view. Just show it from your.
Okay.
And then that's probably what's happening due to bandwidth. So I would share your slides, just don't click slideshow view. Advance them that way. That's just an option.
Mengyue, do you want to try? Yeah. Just exit the.
Okay. I think it worked now. Okay.
Is it? Okay.
Okay. Sorry.
Oh, no worries. It happens. No worries.
Okay. Electro-optic modulator is responsible for encoding data from the electrical domain to the optical domain with high fidelity. EO modulator usually are the originator of EO performance bottleneck at the transmitter in optical links. In a typical commercial coherent transceiver, the modulator donates over 70% of power consumption, introduces half of the insertion loss, and occupies about a third of the area. Obviously, the biggest bottleneck of the transceiver module is the modulator. So we are looking for our integrated platform that can provide high performance overall electro-optic performance. Silicon photonics can leverage the mature silicon CMOS processing techniques, high density integration, and wafer level fabrication, and make a much lower cost. In the very beginning, wireless silicon devices are developed one by one. After that, research start to integrate silicon devices into hybrid module. With the maturity of silicon photonics, silicon chips can compatible with multifunctional photonics device and electronic circuits. But the silicon is symmetric crystal and lacks linear EO effect, so silicon modulator rely on the plasma dispersion effect for modulation. The modulation bandwidth is limited by the time of swapping the carrier and the capacitance of phase shifter. Besides, the EO modulation process of silicon is intrinsically nonlinear and absorptive. Lithium niobate is one of the most popular EO material due to its linear EO effect with fast second time scale response and large EO coefficient, also the wide transparency window. However, traditional lithium niobate modulator rely on the titanium diffuse or proton exchange waveguides on bulk crystal. This weakly confined waveguide make the traditional lithium niobate impossible to enhance the performance of the modulation efficiency, footprint, and EO bandwidth in the future. In recent years, the lithium niobate platform has come to hard research, and we can find you can break the bottleneck and diminish the potential for large scale high density integration, and you also break the bottleneck for the modulation efficiency and device length, also the EO bandwidth. Therefore, we want to combine silicon with lithium niobate, explain the progress effects. The hybrid silicon and lithium niobate material system enjoys the scalability of silicon photonics with the excellent modulation performance of lithium niobate. A few demonstration of hybrid silicon and lithium niobate optical modulator has been reported, all of which rely on the rib-loaded waveguide or SOI bonded waveguide with unpatterned lithium niobate membrane. So the light is reconfined in this hybrid waveguide, and there is a limited overlap between optical mode and active modulation material. So we demonstrate a hybrid modulator in 2019. The high-speed modulation happens at the top lithium niobate membrane. The straight lithium niobate waveguide are dry-edge and highly confined, which is the key to realizing high modulation efficiency. The bottom silicon layer includes all passive components such as MI couplers and grating couplers. The vertical diabatic couplers were formed by silicon inverse tapers and superimposed lithium niobate waveguides, which serve as an interface to couple light up and down between the two layers. We can see in the profile C, the modulation region, it is a lithium niobate rich waveguide showing high overlap between the optical modes and the active material, the lithium niobate. The optical power transfer from the silicon waveguide to the lithium niobate waveguide through VSC, and the calculated coupling efficiency is larger than 99%. we can see the width of the VC tip can be further increased to be more than 200 nanometer. And also there is a large alignment error, which means our technique is compatible with standard lithography tools. A standard SOI processing include the e-beam lithography and dry etching process was used to fabricate the silicon photonics and lithium ion samples with silicon substrates was free bonded to the SOI wafers using the BCB adhesive bonding process. Then the substrate of the lithium ion was removed by mechanical grading and dry etching. Then the waveguide patterns were transferred to lithium ion with optimized argon plasma etching. Finally, the sharing wave electrodes were patterned through a litho process. Optical loss is essential for the modulator to meet the tight budget. Here we measure the propagation loss of the lithium ion waveguide and the carbon efficiency of VSC using the carbon meter. We can see the loss of VSC is estimated to be 0.40 dB and linear fitting shows a propagation loss of 0.98 dB per centimeter. And now we have reduced this value to about 0.1 dB per centimeter. We demonstrate hybrid silicon and lithium ion modulator with on-chip 50 ohm terminator. The on-chip terminator makes the terminator matching with compactness easier, especially for multi-channel modulator. It can also reduce complexity of packaging and testing. And we also use the formal optic bias controller is patterned in the same fab process as the on-chip terminator. Besides, lithium ion is well known for its drifts in the DC bias electro film. So here we use the formal optics effect for stable bias control. The nickel communion metal is on one side of the silicon waveguide to induce phase difference between the two arms. The TO phase shifter is designed for high efficiency and high fusing current. In this work, we can tune the modulator between the on and off state with a power distribution of 24 milliwatts. And for a high bandwidth lithium ion modulator, we should realize the low RF attenuation, good velocity matching, and good impedance matching at the same time. The simulated results for this work are shown here. We can see we have met these three methods. We fabricate a 12 millimeter long modulator featuring a VPI of 2.2 watts, and the modulator reached 3 dB yield bandwidth of 60 gigahertz and low reflection when using the on-chip 50 ohm terminator. We have confirmed that using our on-chip terminator can obtain a decent high frequency response as commercial off-chip load through probes. This modulator can support the 100 gigabaud OK and 60 gigabaud POM4. The data rate is up to 120 gigabit per second. However, we use an electrical amplifier here because the VPI is still not low enough for driverless performance. We can achieve CMOS compatible driving voltage by increasing the device length to about 2 centimeters, but such a standard modulator is not suitable for packaging modules. Therefore, we propose through the MGM to balance the trade-off among device length, yield bandwidth, and driving voltage. Here, the optical arms of MGM and traveling wave electrodes undergoes 180-degree U-turns, thereby reducing the length of the phase modulation region by nearly 60%. And to avoid the phase shifter in the lithium niobate arms being cancelled out after the U-turns, the second wave guide before and after the second wave need to cross here to ensure that phase difference continue to accumulate. By matching the time delay of the optical and microwave U-turns, a perfect velocity match between the optical wave and the modulation microwave can be achieved over the entire modulation region, leading to a large modulation bandwidth. We can observe the yield response of the floating MGM is only slightly worse than that of the non-flooded one once the time delay matches. And to further reduce the VPI, we fabricate the floated device with a total modulation length of 21 millimeter, whose actual device length is 8.7 millimeter. And the measured VPI is 1.24 watts, and the 3 dB yield bandwidth is 40 gigahertz. We realized the 56 gigabaud pump modulation and driverless OK modulation. We modulated the device without the electrical amplifier, and the driving peak-to-peak voltage is as low as 350 milliwatts. The device also features a low on-chip loss of only 2.9 dB. In summary, we demonstrate a hybrid silicon and lithium niobate modulator with good overall performance. We also investigate the floated modulator with a short length but maintain good bandwidth voltage performance. The floated structure provides great design flexibility, especially for building compressed silicon and lithium niobate photonics integrated circuits, because most of the silicon devices are very compact in footprint. That's all my presentation. Thank you for your attention.
Right. Thank you so much for your presentation, Dr. Xu. Do we have quick questions from the audience? Let's wait for, say, 10 or 15 seconds. If no, then we'll proceed to the third speaker, okay?
Okay.
Excuse me, may I have a question?
Yes, please.
Thank you very much for your nice talk. I'm wondering the maximum bandwidth that you can achieve with this MCM modulator. What's the limit of the maximum bandwidth? You show the 100 gigabaud for the OK modulation, but what's the maximum?
Dr. Xu, one of the audience asked you about the maximum bandwidth of your modulator.
The bandwidth. Okay. For the CMOS compatible driving voltage, if you want to achieve 1 volt half VPI, the bandwidth maybe can achieve over 50 gigahertz. And we have a new design now, but it's not a hybrid silicon and lithium niobate platform. We demonstrate over 100 gigahertz 3 dB bandwidth in monolithic lithium niobate platforms, and 1 volt voltage driving voltage.
Thank you. So a follow-up question on that. So what's the limitation for that bandwidth? Like, can it go beyond 100 gigahertz? Like, is it limited by the RF circuits or what else?
Okay, I think I can share one more slides to show that. if we can have to remove the substrate below the sharing wave electrodes, then we can reduce the dielectric loss, and we can replace the regular sharing wave electrodes to the capacitance loaded sharing wave electrodes. Then we can have lower conductor loss. In this way, we can significantly improve the bandwidth voltage performance. We have demonstrated this work in OFC. We can see this work. We have 1 watt VPI, and we can see at the 50 gigahertz, the low off is only 2 dB, and the expected 3 dB. Here we can see it's only the 1.5 dB, and the expected 3 dB yield bandwidth is larger than 100 gigahertz.
Yep. So basically, it's the RC time constant of the RF circuits.
Yes. Maybe we need to do more techniques to remove the silicon substrates.
Yep. Thank you. That's clear.
Okay, so if we do not have more questions for the speaker, then
I had a question, so I don't know if there is time. So the loss from silicon to nitride transition, I think you showed very low loss. Is that measured? Because my understanding is that you're tapering the silicon, but the lithium niobate, it's not tapered. So there will be some loss. Have you measured the loss from transition in between nitride and
Yes.
lithium niobate?
Yes. Thank you for your question. We measured the vertical adiabatic coupler is 0.14 dB for per VAC. The silicon, it has the inverse tapers, and the lithium niobate waveguide is a single mode waveguide. So the coupling efficiency is very high here.
Okay, thank you.
okay. So I guess due to time limitation, we had to proceed to the third presentation. We may come back to further details during the Q&A session afterwards. All right. So our third speaker will be Mr. Taichiro Fuki. The title of his presentation is Single Pixel Imaging Using Multimode Fiber and Silicon Photonic Phased Array. Mr. Fukui received the BE degree in Electrical and Electronic Engineering and MS degrees in Electrical Engineering and Information Systems from the University of Tokyo in 2018 and 2020, respectively. He is currently working towards his PhD degree in the same department at the University of Tokyo. He has been working on silicon photonic optical phase arrays for optical sensing. His current research interests include optoelectronic devices and photon integrated circuits for optical sensing and optical communication, as well as photon devices based on metal surfaces. Since 2021, he is a research fellow of the Japan Society of the Promotion of Science. He's a student member of IEEE, Optica, and Japan Society of Applied Physics. He received the Honorable Mention Award in the Corning Outstanding Student Paper Competition at Optical Fiber and Communication Conference 2020. Without further ado, let's welcome the speaker. So, Mr. Fuki, please go ahead.
Yeah, thank you very much for the very kind introduction. Do you hear me?
Yes, please go ahead.
Okay.
Thank you.
Yeah, great. Okay, thank you. Yeah, so I am Taichiro Fukui from the University of Tokyo, and first I'd like to thank the organizers of this great event for giving me this great opportunity to share about our work on which is published in the JLT. And and I also like to thank my colleagues for this work. So let me first briefly introduce about our lab. I'm a PhD student in this Nakano and Tanemura lab, and basically it's head by these two professors, Professor Nakano and Professor Tanemura, and we're basically working on these integrated photonic device and for optical communication, optical sensing, and optical information processing, and yeah, so we have these. We are like basically working on these optical characterization and device fabrication sometimes, but yeah, recently, due to the silicon photonic foundries available, more of kind of a complex system like experiment is possible now, and we are working on. So this is like some example of our works. So today I'm going to talk about our paper, a JLT paper on this single pixel imaging using multimode fiber and silicon photonic phased array. Yeah, if you have any interest, you can refer to our paper, which I think the organizers have sent you in the invitation mail. And so let me briefly introduce about the background. Imaging through multimode fibers is like kind of seen as the enabling technology in the field of the in Bible imaging. Basically, this diagram compares the multimode fibers with conventional endoscopes. So compared to the conventional micro-objective-based or rod lens-based optical microscopes, the multimode fibers are very thin, and they can kind of have a very minimal invasiveness while maintaining sufficient number of spatial resolution. So they are very useful for observing deep neural activities in the deep brain or something like that. And this is like a very nice example of in Bible imaging using multimode fibers. So yeah, so due to their very minimal invasiveness and the high spatial resolution, multimode fibers are very a great candidate for endoscopic imaging. And so this briefly reviews the how we acquire images through multimode fibers. So basically, many of the methods that is used to acquire images through multimode fiber is classified as single pixel imaging. Basically, what we do is we get a light source and we modulate the wavefront of the input lights and couple that to the multimode fiber. And at the distal end of the fiber, you illuminate the target by set of illumination patterns. Basically, the most intuitive pattern is the raster scanning, but you can also use the speckle patterns but anyway, you kind of switch the input wavefront and get a variety of output wavefront and illuminate that to the target. And you get a return signal from the target, for example, fluorescence or reflection. And then you collect that through the same multimode fiber and detect that by a photodetector to get the power corresponding to the illumination patterns. And you can reconstruct the image by doing signal processing, combining the detected power and the illuminations. And so anyway, you need to kind of have some kind of a wavefront modulator to get these variety of output wavefront. But in current systems, they use this so-called spatial light modulators to modulate the wavefront. And basically, well-known devices include DMDs, digital micromirror devices based on MEMS, or liquid crystal-based devices. And basically, their operation speed is limited to 1 to 10 of kilohertz. And currently, that is limiting the frame rate of the imaging system because basically, you need to modulate the wavefront many times to acquire a single image because a single wavefront pattern corresponds to the 1 pixel of the image. So so in order to improve the modulation bandwidth, the frame rate, we need to get a device with a higher modulation bandwidth. And so our approach is to use the optical phased arrays to generate the wavefront patterns. And basically this optical phase array is very widely studied in the field of integrated photonics. And they are very high speed, but potentially high speed because they can operate beyond gigahertz by employing the electro-optic phase shifters available. And also they're ultra compact, it can be smaller than a centimeter square to with potential integration with light sources and detectors. And although these kind of devices are very actively studied in the beam steering field, here we show that this kind of device can also be used for like imaging through multimode fibers. And in this work, we experimentally demonstrated such feasibility. So this is the schematic of the proposed imaging scheme. Basically, you have optical phase array. You couple input light to the chip, and we distribute the light to n waveguides through a 1/n splitter. And then we phase modulate the light in each waveguide through phase shifters. And it couples to 3D waveguide. And this 3D waveguide is like a kind of a, it's like a 3D waveguide fabricated by, which is inscribed inside a glass chip by optical pulse train. This kind of a chip is available from this company called OptoScribe. And then this 1D array is rearranged to a 2D array to efficiently couple to a multimode fiber. And through the multimode fiber, this wavefront is kind of distorted, and we get these kind of random speckles at the output. And I should note that these random speckles are sufficient for acquiring image anyway. And we can switch these illumination patterns by changing the driving signals of the phase shifters. And we illuminate this patterns to the target, and then we collect the transmitted light through the target and detect the power that transmits through the target. And here we show the use of the transmitted light for the ease of experiment, but we can do the same imaging. We can perform imaging using the reflected light in a similar manner. And so once we detect the transmitted optical powers, we can reconstruct the image by computation and by pre-acquiring these illumination patterns. So we basically in the calibration step, we acquire these illumination patterns, and we kind of use the pseudo inverse matrix to get the original image. So let me briefly explain the image reconstruction process. The transmitted optical power is given by the inner product of the illumination intensity distribution and the transmittance distribution of the target. So here you can see that basically the total power of the light that transmits to the target is like an integration of the illumination intensity and the target transmittance distribution. And when you discretize it, you get, basically it means that you get like an inner product of it. The transmitted optical power is the inner product of the illumination intensity and the target transmittance pattern. So once you get like a bunch of illumination patterns and the corresponding signal powers, you get like if you get K patterns, then you get a K simultaneous equations, and you can solve this equation by using a pseudo inverse matrix. And so basically you get these illumination patterns, which you know beforehand of the imaging step, and you illuminate the target, and you get the signals, and you solve some kind of an inversion problem to get the image. So this is the silicon optical phase array chip that we have fabricated. Of course, the chip was fabricated by a foundry. Basically, it has the input light, and it distributes the light to 128 waveguides. And and this is so each waveguide has a 250 micron long fermo-optic phase shifter, and here we use the fermo-optic phase shifter due to like the limited resources, but of course in the future we can use the PN junction phase shifters to get a very high modulation speed. So yeah, we fabricated this kind of a optical phase array, and so this is like the schematic of the 3D waveguide, and basically we have 128 input waveguides, and it's like a 1D array. While through the 3D waveguide, it's converted to 2D pattern to the array to be efficiently coupled to the multimode fiber. And this fiber supports 557 modes per polarization, and this is the experimental setup. So basically, you have a laser light source, and then we polarization control it to a T mode and amplify it, pre-amplify it, and we got an optical bandpass filter, and then we couple it through lens fiber to the chip, and then we align the optical phase array to the 3D waveguide, and of course, this optical phase array is controlled through a driver circuit, and through the multimode fiber, we get the output light, and we image this relay this near field pattern, the near field pattern of the multimode fiber output through two cascaded fourth systems, and we illuminate this to the target and get the transmitted optical power, and we monitor the far field pattern, the near field pattern of the multimode fiber simultaneously using the INGAS camera. And yeah, here we can see that we have experimentally acquired these illumination patterns, and we can see that by tuning the phase shifter condition, we can finally modulate the output wavefront. And yeah, this is the imaging result. You can see that the by increasing the number of patterns of the illuminations, you can get a fine image of the target. And yeah, and one interesting thing is that this quite nice image was obtained just by using only 128 phase shifters, which is you know, so given that this image has a pretty nice resolution, we despite using only 128 phase shifters. And to quantitatively evaluate the number of resolvable points, we derived the point spread function of the you know, the system by numerically imaging the infinitesimal target using the experimentally acquired illumination patterns. And you can see that the full width half maximum was approx 3.3 micron. And this was almost uniform over the entire multimode fiber core. And the number of resolvable points was estimated to be around 1,000 points from here. So so like 1,000 points can be resolved despite using only 128 phase shifters. And this is like a kind of an interesting point. And we also confirmed this point through the singular value analysis of the illumination patterns that we got. So this kind of, yeah, and this singular value, like, you know, the singular value of this illumination matrix actually corresponds, describes like the spatial resolution of the, or like the number of independent patterns involved in the matrix. And, you know, we derived the singular value decomposition of the experimentally acquired illumination matrix. And basically, you know, we got like a very large number of the singular value index with a non-zero value. Although, and this purple line corresponds to like using a 1D uniform optical phase array, and this is pretty limited. And by using the multimode fiber, and in fact, we can enhance spatial resolution. So, and due to the time limitation, maybe I'll omit this point, omit this slide. But we did some more detailed theoretical and numerical study on the number of resolvable points available through system in this Joseph paper. So you can also read that paper if you have any interest. So as a summary, we have experimentally demonstrated single pixel imaging through a multimode fiber using an integrated silicon photonic optical phase array chip. And yeah, so we fabricated this 128 element from optical phase array, and we combined that with a 3D waveguide to generate illumination patterns through a multimode fiber. And using that illumination patterns, we have experimentally acquired a very nice image. And also the interesting point is that we can get a quite large number of visible points with only 128 phase shifters. And that's very nice because so first you need to have a very densely, so if you need a very large number of phase shifters, that's pretty challenging to control. And so, yeah, in that sense, this is a very nice feature of this scheme. So yeah, this work paves the way towards the ultra high speed and compact multimode fiber based imaging systems. Yeah, so thank you for your nice, kind attention.
All right, thank you so much for this wonderful presentation. Do we have questions from the audience? Actually, I saw a question in the chat box. Yeah, so one question is related to your research. Why we use multimode fiber over single mode fiber for this research? Can you answer this question for the audience? Thank you.
Okay, yeah, thank you for the nice question. So basically, the point of using the multimode fiber is like the number of spatial modes that's available through like a same diameter. So if you use the so of course you can use a bundle of single mode fibers, but that will end up with a very large endoscope, and that's not applicable for like that will not give a sufficient number of visible points with a available diameter. For example, so you can see that for example, in our work, we use like a multimode fiber with a core diameter of 0.125, and that gives like a 557 modes, spatial modes. But given that, if you use a single mode fiber, then like the core diameter is several microns with only one spatial mode. So even though you densely pack them with and make a mod bundle with them, you cannot get like a comparable spatial resolution.
Okay, thank you. So basically, you just want to make the imaging system more compact.
Yes, that's true. Yeah,
okay.
Yeah, that's the advantage of the multimode fiber over other methods.
Okay, thank you.
Yeah, thank you very much.
Do you have more questions for this speaker?
That there was one from Professor Mahdi, but I'm not sure if that was already answered.
Let me see. First more.
So all of the parameters for the fibers are considered as optimized values.
Thank you very much for the question. So in that sense, yeah, that's an interesting question. So,
and he did follow. It was followed up that I believe it had been answered, as it was mentioned in the more compact imaging system. If you have a way to elaborate on that.
Yeah. So maybe maybe another thing to add to the previous answer is that maybe we can get a higher numerical aperture fiber so that we can improve the number of spatial modes with the same diameter, but we haven't done that yet. So in that sense, yeah, this is it's like a proof of concept demonstration. So we haven't like kind of truly optimized the configuration in depth. I mean, yeah, we just chose it due to some balance of like the available optical phased array and available 3D waveguides and so on.
All right, I see one more question coming from the chat box. What's the future work for this study?
Yeah, thank you for the nice question as well. So like one thing we have to do is like we need to image through the fiber using the reflected light because of course as an endoscope it needs to use the reflected light. So yeah, that's one thing we haven't achieved yet, but yeah, one natural step to go forward is to use the reflected light, and I believe that that's possible by using like a micro lens system at the input side of the fiber. And also another step is to use the carrier depletion type or carrier injection type optical phase shifters so that we can, clearly outperform the conventional spatial light modulators in terms of the frame rate. Okay, thank you very much.
All right, thank you. So probably since you were finished your presentation, you can probably look at this chat box directly. So one more question. Would using pulse laser in such multimode fiber imaging be helpful for ranging in addition to recovering the face mask, or will it lead to issues with reconstruction?
Wait a moment. So thank you for the question. Yeah, the use of pulse laser is actually very interesting, but one thing we have to be careful or to treat about is like that the modal dispersion and the dispersion of the transfer matrix of the multimode fiber is pretty large. So it depends, I think, on the length of the multimode fiber, but we need to kind of be careful about that point. And in fact, I know some papers that uses short pulse lasers coupled to a multimode fiber to generate like a series of like speckle patterns because by through modal dispersion you get like these bunch of different output lights with the same input due to the dispersion. So in that sense, if we want to use like a really short pulse laser, we need to be careful about that point. But of course, I think by using like a moderate short pulse laser and also the use of the very short multimode fiber because the fiber doesn't have to be ultra long. I mean, because we just want to use it as an endoscope. So yeah, in that sense, it could be useful. I mean, because for example, if we want to use it for nonlinear imaging or something like that, then we need a high peak power and so on.
Okay, yeah, thank you very much for answering. So we are actually running